Our speaker today is Michael Barrus, and he will be talking on the Erdős-Gallai differences of the degree sequence. The stage is yours, Michael. Thank you for giving us talk.
Thank you very much, Sandra. And I want to thank all the organizers for having me and for everyone for being here. I see some good friends in the audience. Thank you very much for coming today. I want to talk today about degree sequences. So I think we know what a degree sequence is. The only thing I'll really emphasize here is that everything I'm going to talk about is about a finite simple graph, and our degree sequences will always be ordered from largest to smallest. So with that preface, I'll define the modified Durfee number. This will be important to us. And this is just the last index for which the ith degree is at least as large as I minus 1. So if we were to take a look at this degree sequence here, we might just start counting 0, 1, 2, 3, and we're going to pay attention to the last place where the degree is at least as big as the number we're calling out. So we'll call out 0, we'll call out 1, we'll call out 2, and then if I call out 3, I'll see that we've gone too far. So 3 is our modified Durfee number for this degree sequence. And once we've defined the modified Durfee number, the principal Erdős-Gallai differences are what we'll call these functions of k. Now, k is going to be somewhere between 1 and the modified Durfee number. And then for each delta sub k, what I mean is k times k minus 1 plus a sum of some function of the degrees minus some other degrees. And let's make sense of this using our example above. So I'm going to compute delta 1. And what I'll do is I'll insert the 1 times 0, but then I'm actually going to jump to the end here, and I'm going to pay attention to the first k degrees, which remember are the largest k degrees, and I'm going to subtract them. So if k is 1, I'll subtract the first 2. And then for each of the remaining degrees, I'm going to go through and I'm going to record either the degree or k, whichever is smaller. So as I go through the rest of these, I'll record a 1 in each case because 1 is at least as small as the degree terms. So we add these pieces together, we get a total of 2, and that's the first Erdős-Gallai difference. All right, now you could do this for k equals 2 and k equals 3, or however many you needed to reach the modified Durfee number. And I'm going to use delta of d to stand for the list of these principal Erdős-Gallai differences. Okay, so what is this? Why do we talk about this? I mean, this graph has Erdős-Gallai difference list of 2, 2, 2. Does this tell us anything? Well, where these come from is from the Erdős-Gallai criteria for recognizing whether a list of non-negative integers is a degree sequence or not. So I'll remind you that if we assume these are all non-negative, and if we order them from the largest to the smallest, and if it's true that it has an even sum, that's also something you can't ignore. Then if those things are in place, your list of numbers is the degree sequence of a graph if and only if these inequalities hold for all k. So you'll see here on the left, we've got the sum of the largest k degrees. And then on the right, we've got some very familiar terms here. And what's happening, if you imagine that you have a set containing the k vertices of highest degree, or some k vertices of highest degree, the left-hand side records how many edges sort of start at one of these vertices. So they're kind of the halves of edges that begin in total in this set. And then on the right-hand side, what we have are sort of upper bounds on the capacity for these edges to find an ending place. So some of these edges might actually meet up inside that set. They might be paired up together. And so an upper bound for how many times that can happen is 2 times k choose 2, which gives us that term there. And then for these vertices outside the set, they could potentially be adjacent to as many as their degree will allow, but no more than that. And they also can't be adjacent to more than k of these vertices because there are only k vertices here to begin with. And so that's where we get this, this upper bound on the capacity of the other vertices to receive these edge halves. Okay, so that's a pretty straightforward necessary condition. You know, the interesting part is the sufficiency, and that's actually not what we're going to talk about today. But what I'll mention is that Erdős and Gallai originally stated this with the k's running from 1 to n. You needed to check all of those. But later in 1975 and then later in 1981, Lee and Hammer, Ibaraki, and Simeon showed that you actually don't need to check all n of these inequalities. You can actually just get by checking the k's from 1 up through that modified Durfee number. So we're going to talk about Erdős-Gallai differences, not so much these inequalities, but you'll see that the difference is exactly how far apart the right-hand side and the left-hand side are from each other. That's where we get our expression for the kth difference. And what we get is that if we're talking about a degree sequence, every one of these Erdős-Gallai differences is going to be non-negative, right? All right, now I'm going to hopefully convince you over the next few minutes that these are interesting to look at. And I will mention the first times they showed up. So this isn't original to me. These differences showed up in 1975 in papers by Karen and Lee, although Lee's definition, they had the opposite sign from what we have. They were both using these Erdős-Gallai differences as a means of studying graphs with a unique realization, degree sequences with a unique realization. But in effect, they used these Erdős-Gallai differences to simplify degree sequence recognition. So without going into too much detail, I'll just remind you that we have a degree sequence if and only if these differences are non-negative for all indices. And what Lee did is he showed that if you're looking at the differences, and if m stands for your modified Durfee number, then the differences from the mth term on are all, they form a strictly increasing sequence. So if what you care about is that they're non-negative, you actually don't need to check any of these later ones. You only have to check the first difference up through the mth difference. And that's where we get that reduction from the previous slide. Lee also showed a couple of other things. One of these is that if the first term happens q different times before you start moving on to smaller degrees, and if the qth difference happens to be non-negative, then you also don't need to check the earlier ones. They will also be guaranteed to be non-negative. So other authors have come along later than this, and they've shown that there are even more inequalities you can leave off. There are fewer that you have to check to see if it's a graphic sequence. But I'll just point out that these results kind of work by showing how the Erdős-Gallai differences are related to each other. All right. Now, the differences also show up when we talk about split graphs. So Hammer and Simeon in the early 80s studied the split in subgraph. And I'll remind you that a split graph is a graph whose vertex set can be partitioned into a clique and an independent set. So all edges possible are present in the clique and none of them are present in the independent set. And if we ask about the splittance, what we're asking about is how far a graph, an arbitrary graph, is from being split. So S of G, as I'm calling it, is basically the edit distance to the class of split graphs. And we measure edit distance in terms of edges or non-edges that need to be tweaked. So you'll see that in this graph here, if I were to erase that solid edge and fill in that missing dotted edge, then the black vertices would form a clique and the white vertices would form an independent set. So this graph has splittance at most 2, and it turns out to be exactly 2. What does this have to do with the Erdős-Gallai differences? Well, Hammer and Simeon gave a formula in terms of the degree sequence for the splittance of a graph. And they didn't exactly state it in terms of the Erdős-Gallai differences as I'm defining them, but it turns out to be equivalent. So stating it in the language I want to use today, they showed that if D is the degree sequence of any graph, then the last of the principal Erdős-Gallai differences is exactly 2 times the splittance. And so we see a 4 here, and half of that is 2, and lo and behold, the splittance was 2. Now, that's kind of interesting. What I find particularly interesting is that on the left, you have a function of the degree sequence, and on the right, you have a function of the graph. And you know that most degree sequences have more than one realization in terms of graphs. And so any graph having a particular degree sequence is going to have the same splittance as any other graph having that same degree sequence. It's kind of an interesting property, this edit distance from the class of split graphs. Okay, but the Erdős-Gallai difference, the last one in particular, makes an appearance. And as a corollary, we get a characterization of the split graphs themselves. And it turns out a graph with degree sequence D will be split if and only if that last of the Erdős-Gallai differences is equal to 0. The last principal Erdős-Gallai difference is equal to 0. All right. So again, their characterization wasn't written in terms of the difference, but you can write it in terms of the difference, which I think is kind of a theme, as I'll show. If we move on to another graph family, the threshold graphs are defined in a bajillion different ways. They've got many different equivalent characterizations. The one I'll pull out today is that a threshold graph is a graph that is the unique labeled realization of its degree sequence. So if I were to say that this vertex had degree 4 and 3 and 2 and 2 and 1, and I didn't show you the edges, if you were to match up the vertices so to make the degrees what they should be, you would be guaranteed to get this picture. You really have no choice at all. There's only one labeled realization. Right, Hammer, Ibaraki, and Simeon gave a characterization in terms of degree sequences for threshold graphs. And their characterization was basically that equality held in the Erdős-Gallai inequalities, which for us is the same as saying that the difference is equal to 0 rather. And that needs to hold for all of these principal Erdős-Gallai inequalities. So this degree sequence here, if we form its Erdős-Gallai difference list, we'll end up with 0, 0, and 0. And that's how we recognize, that's one way of recognizing that this is a threshold graph. All right, well, given what we know about split graphs and threshold graphs, a few years ago, I was starting to think about these Erdős-Gallai differences, and then I just wondered, what's the next step? So I just, for the heck of it, defined a graph to be a weakly threshold graph if its degree sequence had the property that all of the Erdős-Gallai differences were less than or equal to 1 as you ran over the first M of D of those degree differences. And so here's an example of what I call a weakly threshold graph. Here's its Erdős-Gallai difference list, and you'll see that every difference is 0 or 1, which was our definition. Now, I won't take too much time to get into this here, but one of the nice things about this class of graphs is that for many of the equivalent characterizations of threshold graphs, you can find a more general statement that characterizes the weakly threshold graphs. So if you're talking about forbidden subgraphs, there is a forbidden subgraph characterization of this class. There is a degree sequence characterization we've mentioned. There's also a nested neighborhood or an iterative construction characterization. There are a lot of nice generalizations of the properties of threshold graphs that are held by these graphs that satisfy a slightly weaker condition on the Erdős-Gallai differences. Okay, now moving away from graph classes for just a second, the differences kind of show up in work by some other authors. Tishkovich in 2000 published an English language version of some papers she'd written in the 1980s, and Karen in 1975, he also looked at what happens if you ever find an Erdős-Gallai difference equal to 0. Now, I believe Karen actually was talking about the differences. So what you see when that happens, remember what we said, that if the very last of these principal differences was equal to 0, then you're looking at a split graph. If one of the earlier differences equals 0, then what happens is if k is the index, the k vertices of the largest degree form a clique. And any vertex, well, all of the vertices whose degrees are strictly less than k, they're forced to form an independent set. And then any other vertex there is in the graph is forced to be adjacent to all of the vertices of the clique and to none of the vertices in the independent set. And this happens not just in split graphs or, this is an arbitrary graph kind of statement. It happens when your Erdős-Gallai difference is equal to 0 somewhere in that list. All right, now in a different problem, let's change gears yet again. A couple of years ago, I and Brian Cloteau, we were independently looking at the same problem. We were looking at all of the labeled realizations of a degree sequence. So if I were to take a very simple degree sequence, it turns out that there are 2 realizations that have the top 2 vertices having degree 2 and the bottom 2 vertices having degree 1. And in general, if you look at a degree sequence and you look at all of its possible labeled realizations, for most pairs of vertices, you're going to find one realization where they're adjacent and another realization where they're not adjacent. Okay? But sometimes, if you're lucky, you'll find a pair of vertices that happen to be adjacent in every single one of the labeled realizations, like these top two vertices. And I would call that a forced edge. And sometimes you'll find two vertices that are not adjacent in every single one of the labeled realizations. And I would call that a forced non-edge or non-adjacency. So we kind of took the research in different directions in our papers. In my paper, I looked at the Erdős-Gallai differences and showed that this behavior of a forced edge or a forced non-edge requires that one of the Erdős-Gallai differences be 0 or 1. Okay? And so this was a major impetus to my wanting to look at the weakly threshold graphs, which require this everywhere. Okay, so having talked about classes of graphs, having talked about simplifications in testing for graphicality, talking about forced edges or whatever, I think that these Erdős-Gallai differences are maybe something, the start of something. There's more we should look at as we take a look at these properties that seem to have something to do with this Erdős-Gallai difference list. And so today I want to take a look at two particular problems. And the first one has to deal with the complement of a graph. For many of these properties that we've mentioned, it turns out that a graph has that property if and only if its complement has that property. So if the graph is split, its complement will also be split. And that's pretty clear to see from the structure. You know, the complement is going to change a clique into an independent set and vice versa. Now, for a threshold or weakly threshold graph, you can see this in a couple different ways. One of the easiest ways is to look at their lists of forbidden subgraphs. And each of their lists of forbidden subgraphs is closed under complementation. So that kind of gives you the result. Now, when a graph is decomposable in the way of Tishkovich and Karen, you can sort of tell from its structure that the complement will also be decomposable. And when you have forced edges or non-edges, if you were to take the complement, a forced edge turns into a forced non-edge and so on. And so we've got lots of reasons why these things should satisfy this complementary property. But I'm interested in these Erdős-Gallai differences. And given that the Erdős-Gallai difference gave a way of characterizing each of these behaviors, I might wonder if there's a direct connection between the Erdős-Gallai differences and this complementarity idea. And so I want to answer whether it's true that the Erdős-Gallai differences of a graph and of its complement have anything to do with each other. And you can see from this example that it's not an immediate answer. We don't see that they have the same length or even the same values. I mean, they do have some similar values, but not all of them. So maybe there's something to say here. Another thing I want to get to before the end of the talk is this connection to majorization. Okay, so for those of us in the audience who are fans of threshold graphs, you know that when you take the partitions of a given number, so here we're taking the partitions of 10, and when you ignore all of them except the partitions that actually are degree sequences of simple graphs, then we can order them by majorization order. And I'll say that one degree sequence D majorizes a degree sequence E if the kth partial sum of D is greater than or equal to the kth partial sum of E for all K. And I'll just remind you that these degree sequences are ordered from largest to smallest. So when I add the K largest terms of D, I will always get a sum that is at least as large as the K largest terms of E. And you can kind of observe that as we compare these things. Things on the bottom half here certainly start out slower as we're looking at partial sums than things at the top. All right, so we've got a cover diagram here. Threshold graphs, split graphs, weakly threshold graphs, decomposable graphs, and graphs with forced adjacencies or non-adjacencies, they all form upwards closed sets in this poset. So as I was saying, threshold graphs are exactly the graphs whose degree sequences are the maximal elements of this poset. once you fix the number of edges and you form this majorization poset, the maximal degree sequences there are going to be precisely the degree sequences of threshold graphs. Now, Mara showed in 2003 that if I take the degree sequence of a split graph, then any degree sequence that majorizes it will also have that property. They'll all be split. So we get that the split sequences form sort of an upward closed set in any of these posets. And then I showed that the same property is true for weakly threshold graphs. And the same property is true if you ever run into a decomposable degree sequence. The degree sequence of a decomposable graph, there's that property is upward closed. And forced edges also turn out to be present in one sequence if and only if, well, sorry, not if and only if, but if they do show up for one degree sequence, they also show up for every degree sequence above it in the majorization order. All right, so these very, not necessarily related to each other properties, they all have this similar property in the majorization order, and they all have a relation to the Erdős-Gallai differences. And so I wonder if there's a direct connection between the Erdős-Gallai differences and the majorization poset. And as you take a quick look at the Erdős-Gallai difference list, which I've kind of written next to all the degree sequences, I think you'll start to see there probably are some very clear patterns to those Erdős-Gallai difference lists if you look at them through the lens of majorization. So those are the questions I want to answer in the remainder of the talk. And to get started, I want to introduce a tool that will be helpful. The corrected Ferrers diagram is something you can build from a degree sequence. And I'm going to write it as a matrix. It's not always written as a matrix, but that will be useful for us today. So let's make an n by n matrix where n is the number of terms in your degree sequence. And let's start by putting a diagonal of zeros down the main diagonal. Okay, and this is in violet. Nothing's going to change the fact that there is a diagonal of zeros from the top to the bottom. What I'll do for the remaining entries is I will fill in the rows with ones according to what the degree tells me. So in the first row, I'll take a look at that first three, and I'll put 3 ones in the first spots that don't interfere with the main diagonal. Then for the second row, I'll put 2 ones. Again, I kind of make way for the main diagonal, but the first 2 spots otherwise are filled in with ones. And I'll do the same for all of the other rows. And then I'll fill the remaining entries with zeros. Okay. Now, one thing that's very helpful, very handy about looking at this corrected Ferrers diagram, and is that if you were to look at what happens if you take the degree sequence of the complement of a graph. So let's suppose that I took a graph having this degree sequence, I took the complement of that, and then I looked at the degree sequence of the complement. I'll be able to kind of tell what that looks like from here. I mean, from the degree sequence itself, I know that this last vertex has degree 1. We know that it's not going to be adjacent to that particular neighbor in the complement. It's also not going to be adjacent to itself in the complement, but all of the remaining zeros in this row will turn into ones as I look at the degree sequence of the complement. Okay. And so if you kind of squint and maybe turn your head a little bit, you'll see the shape of the ones in this diagram traced out in the shape of the zeros in this diagram, and vice versa. It's just that all the ones are changed to zeros, and the matrix seems to have been rotated by 180 degrees. Right? All right, so we'll see that come into play in just a second. But I want to say more about this corrected Ferrers diagram and how it connects to the Erdős-Gallai differences. So you'll remember that our Erdős-Gallai differences take the right-hand side and subtract the left-hand side. And if I take k somewhere between 1 and the modified Durfee number, it turns out that the sum of the entries in the first k rows are exactly the sum of the degrees. That's pretty straightforward to see. And then the sum in the first k columns actually turn out to be the right-hand side here. If you take a look in the first k rows, the ones that are counted are exactly counted by k times k minus 1. And then for the remaining rows, we are adding either the minimum of k or the degree, because we're kind of chopping things off after the kth column. All right, so then if we wanted to look at the Erdős-Gallai differences, maybe what we ought to do is pay attention to the initial rows and columns of the Ferrish diagram matrix. And that's what I'll do. I actually am going to take those first columns and change them into rows by taking the transpose of that matrix. And then I'll subtract off the first rows of the original Ferrish diagram matrix. And I'm going to call that matrix M of D. I'll call it the difference matrix. And this may or may not be new. I haven't run into it in the past, but this is what M of D will stand for. We're taking the conjugate, or the transpose rather, of the Ferrish diagram and subtracting. Okay, so when you do that for a particular degree sequence, you get this picture here. And we did this motivated by the Erdős-Gallai differences. So we would be looking for them to show up somewhere in this matrix. And given that the degree sequence had these differences 2, 4, and 4, as you stare at that, you'll see without too much trouble that what we get are the 2, 4, and 4 from taking the sums of the entries that are left. After we subtracted these, a lot of things cancel each other out. The ones that are left form the difference between the right and the left-hand side. And the 2, 4, and 4 are the partial sums of the rows of this matrix, the entries in those rows. All right. Okay, so that's going to be handy to us. Let's see what we can get with that if we move on to the complementation problem. So are the lists of Erdős-Gallai differences related under graph complementation? And you might wonder if it's necessary to talk about the Ferrish diagrams at all. I mean, we have an expression for the degree sequence of a graph complement. And if I were to plug this in just to our normal definition, can't we just kind of derive some connections in this way? And I won't say that you can't, but I will say that it's not immediate. There is a little bit of shifting of indices, and the things you're minimizing here, well, you're subtracting them, so this could turn into a maximum. You're also kind of looking at the opposite end of the degree sequence. I'll just leave it as something that maybe is not trivial, okay? So what I'm gonna do is take a look at these difference matrices instead. And if I take a look at the difference matrix of a degree sequence D, and if I take the degree sequence of the complement and look at its difference matrix, a couple things will stand out to you. You'll see that the ones here are kind of in a zigzag pattern. We see zigzag of -1s down here. And we see also a zigzag of -1s and a zigzag of 1s. But they're not lying in the same orientation between the two matrices. And if I look at the partial sums by row, I'll end up with 3, 1, 0 if I go all the way down and if I don't stop it after these principal differences. Now, if I look at the differences for the other graph, 1, 3, 4, 4, I'll notice that actually the 1, 3, 4, 4 shows up in reverse order as I kind of count upwards from the bottom of M of D. And the differences for D show up as I count upwards from the bottom of M of D bar. So we'd like to show that actually the differences of the difference matrices of D and of the complement of D are transposes across the anti-diagonal. So normally when we take the transpose, we go across the main diagonal, and I'm going to take the transpose across the other directions, main diagonal. And it looks like these two matrices are related in that way. I also want to prove this fact that the differences of D bar show up in reverse order as I approach the end of the matrix M of D. So here's where that matrix is going to come in handy. Setting this Ferrish diagram as a matrix, I'm going to use the fact that I can get the Ferrish diagram of the complement by rotating and toggling the entries of the original Ferrish diagram. And I'm going to express the Ferrish diagram of D bar then as the all ones matrix minus the identity matrix, which is going to preserve the zeros on the diagonal. Then if I were to subtract the original Ferrish diagram, that will change all the ones to zeros and all of the off diagonal zeros to ones. And then I need to rotate it 180 degrees. And because this anti-transpose has showed up, let me just write that as taking the transpose and the anti-transpose both. And your dihedral symmetries kind of show that that's going to accomplish a 180 degree rotation, right? So if I take this expression for f of d bar, I can calculate m of d bar, the difference matrix of the complement, by just plugging in our definition and substituting in my expressions. And you'll see here we have a couple of transposes. You'll see that the all ones in the identity matrix cancel each other out in this difference. We end up with just the original Farage diagram, transpose minus the original Farage diagram, taking the anti-transpose of that. And so we have proved our first result, that these two matrices are just reflections of each other across that the non-main diagonal, the anti-diagonal. Okay. All right, now let's talk about the Erdős-Gallai differences, because that's what I'm really interested in. Can we say anything about these? Can we show that the differences do, for d bar, do show up as partial sums in the M of D matrix, just in reverse order? And we can, and again, there's a little bit of matrix arithmetic that's going to make this work. I'll just point out that the sum of the kth rows of M of D bar, that's what we get if we just take this vector hk, which is a row vector with k1s and the rest of the terms are 0. We multiply on the left by that row vector and on the right by the all ones vector. That will just sum the entries in the first rows. And then if I use what I know about the anti-transpose, I can get M of D in there instead of M of D bar. And then this is the fun part. We're going to try to handle that anti-transpose, try to get rid of it somehow. And so what I'll do is I'll take this all ones vector, and because it is an all ones vector, if I were to rotate it by 180 degrees, it will still be the all ones vector. And if I were to take one of these h vectors and rotate it by 180 degrees, it would have the zeros appearing before the ones. So if I express hk as 1 transpose minus hn minus k, rotated by 180 degrees, things should still be equal. Okay. All right, but then the transposes can be factored out of everything. And so we'll get a 180 degree rotation of this expression. And then if I remind myself, on the left-hand side, we've just got a scalar. It's just a constant. So rotating a 1-by-1 matrix shouldn't change anything. And so this, we can drop the two transpose and anti-transposes. And then if I go ahead and distribute this matrix through the subtraction, I'll end up with the sum of all of the entries in my skew symmetric matrix. And because it is skew symmetric, that will end up being 0. And again, because M of D is skew symmetric, when I see a minus transpose of that, I can just yank that out and place M of D back in itself. And we end up with the kth Erdős-Gallai difference of the complement ends up being the sum of all but the k rows of the M of D matrix. So we've ended up showing that our partial sums are the terms in reverse order, as we were hoping to show, right? Now that's kind of a nice description of what's going on with this M of D matrix, but it doesn't necessarily answer my original question of, are there any connections between these Erdős-Gallai lists for degree sequence and its complement? And so we'll dig a little bit deeper into this matrix, and we'll take a look at where these partial sums are coming from. We'll also take a look at the fact that in the example we chose, the 2, 4, 4 and the 1, 3, 4, 4, they overlapped. The 4s were common to both of those. And so those 4s do show up in both of those Erdős-Gallai lists, difference lists. And as it happens, that's always going to happen, that the Erdős-Gallai list for D and for D bar are going to overlap on at least one row. And so the very last of the Erdős-Gallai differences will be the same for a graph, a degree sequence and its complement. And then if you take a look at the maximum Erdős-Gallai difference, you'll see that you reach a maximum exactly when you have processed an island. You've reached the end of one of these islands of non-zero entries. It takes a little bit of work to show that these islands of non-zero entries don't overlap or interfere with each other, but it turns out that they don't. And so when you reach the end of an island, the fact that M of D bar is sort of the anti-transpose of M of D means that you're going to reach that end of that same island somewhere, and you'll have the same sum. that you did. It may be in a different position than you did originally, but you'll have the same sum. Okay, so that allows us to conclude a stronger statement than this, but it is true that delta of D and delta of D bar have the same maximum Erdős-Gallai difference as you compare the two. So this is what we need to give another proof of some of these properties we were talking about at the beginning. So in the case of split graphs, remember that split graphs were those where the last Erdős-Gallai difference was a 0, and these were closed under complementation. And you could recognize them because of that last Erdős-Gallai difference, which we just got done showing, needs to be shared as the last term of delta of D bar. So we have another proof that the complement of a split graph is split. Not that we needed another proof, but this proof relies just on these Erdős-Gallai differences. And so we can also use it for other properties as well. So weakly threshold graphs and threshold graphs, these dependent on having none of your Erdős-Gallai differences larger than a certain amount. So your maximum term had to be less than or equal to a certain amount. And that is also a property that is shared by the complement of a degree sequence. And so we have, as a corollary, these facts that we knew before, but now we have a new reason why. And what's more, we don't have to stick with just those examples. So if we talked about all the graphs that had the last Erdős-Gallai difference equal to a certain value or less than a certain value, that's equal to having splittance a certain value or less. It turns out that those graphs are all closed under complementation, which maybe you could have seen already. But what about graphs having a maximum Erdős-Gallai value equal to or less than a certain value? The threshold graphs and the weakly threshold graphs handle this when z is equal to 0 or 1. But if z were anything, you would still have a class of graphs that's closed under complementation. So moving on to our second question. Are there any nice connections between these Erdős-Gallai differences, these lists, and position inside one of these posets on degree sequences? And as we take a look at this majorization list, the answer seems to be pretty positively so. So what we observe here is that if D majorizes E, then any particular difference in any particular position. So we'll say, take a look at the first difference there. Here we have a 0, we have a 1, we have a 2, a 3, a 4, a 5, a 6, and 8. It just seems to grow as you march down. Or if you were to march up, you'd see that those differences in a fixed spot, they tend to decrease. So the higher you get, the smaller the differences get. And that's maybe why you see threshold sequences right at the very top. Now, as you look at some of these, you'll see that the length of these Erdős-Gallai difference list doesn't hold still or doesn't stay monotone as you move up. And so positions, if positions are lined up, we can certainly compare them, but sometimes we can compare things that aren't in the same position. And for instance, if I take a look at the last Erdős-Gallai difference for D and the last Erdős-Gallai difference for E, even if we have different lengths, I'll see that the higher one in the poset is less than or equal to the last one for the lower in the poset degree sequence. And then if we were to not worry about position at all and just keep track of the maximum Erdős-Gallai difference, so 8 and 6 and 5 here and 4 and 3 and so on, the location of the maximum might jump around from sequence to sequence, but the value is monotone as I move upwards. The maximum value in an Erdős-Gallai difference seems to shrink consistently as we move up. All right, now I will just point out that this gives a unified proof, or these three different properties explain why all of these statements hold. Your forced adjacencies, your decomposable graphs, whether a graph is threshold split or weakly threshold, they had everything to do with small Erdős-Gallai differences. And knowing that these differences are monotone, it gives us that these properties are all closed as you look upwards in the dominance order, and the majorization order. All right, so we're not going to get into a proof because of time here, but you know that if you've worked with this majorization order, you know some of the standard tricks. You move from one sequence to another by kind of moving a box, subtracting one from a term and moving it down to another term. And it's through sort of a careful analysis of that, using our matrix M of D, our difference matrix, that allows us to make these conclusions about majorization order. To wrap up, I want to talk about one more degree sequence partial order. And this one is a little bit different in that whereas majorization required your degree sequences to have the same sum, the Rao order works to compare any two degree sequences, no matter what sum, no matter what length. Okay. So SB Rao in 1980 or so defined a partial order on degree sequences. We'll say that D Rao contains E, and these are degree sequences, if D and E have realizations G and H, where G contains H as an induced subgraph. Okay, so in our poset example here, 211 has a realization that's the path on 3 vertices. And if I look up here to 22211, there are multiple realizations, but there's one of them that does contain this as an induced subgraph. And so that would mean that this degree sequence Rao contains this degree sequence. Okay. All right, now Rao showed this actually is a partial order on the degree sequences. It's been shown within the last couple decades by Chudnovsky and Seymour. This is actually a well quasi-order on the set of all degree sequences. This is a wonderful poset for a couple different reasons. And one of them has to deal with any kind of problem involving both induced subgraphs and degree sequence characterizations. You may have noticed that all of our degree sequences, or our graph classes, the threshold graphs, the weakly threshold graphs, even the split graphs, they have forbidden subgraph characterizations. They also have degree sequence characterizations. And what happens is that if you were to forbid the Rao containment of a certain degree sequence, and if you were to exclude all degree sequences Rao containing a certain one, in effect, what you're doing is forbidding a set of induced subgraphs. And so not every set of induced subgraphs corresponds to forbidding a Rao containment, but when you do have that correspondence there, you get some very nice results. So what does this poset have to do with the Erdős-Gallai differences? So I'm going to take a look at 3 sequences, 4, 3, 3, 2, 2, 2, 2 to 2, 1, 1, which is here in this diagram, and then 2, 1, 1, which is here at the bottom. I'll show you that D does Rao contain E, and that E does Rao contain F. Now, if I take a look at the Erdős-Gallai differences, I won't necessarily see immediate connections in the same way that I did for the majorization. The differences in any fixed position can either increase or they can decrease as I move up in the Rao order. And sometimes the length can change. What we can show briefly is just that if D does Rao contain E, then first off, the modified Durfee number is at least as large as it was. If D Rao contains E, then the last of the Erdős-Gallai differences is greater than or equal to the last of the Erdős-Gallai differences. So we'll see that 2 is greater than or equal to 2, which is greater than or equal to 0. And then the maximum, again, it's the last and the maximum terms that seem to be very important to us. That's also true for the maximum. The largest value here of 3 is greater than or equal to the largest value here, which is greater than or equal to the largest value here. Okay. All right, now the first 2 of these are fairly straightforward observations. I'll just remind you that the last Erdős-Gallai difference corresponds to the splittance. And if you think about induced subgraphs, you'll be able to prove this almost immediately. The last statement takes a little bit more work. Again, it's a little bit of careful analysis using the difference matrix, and we get the result. So as a corollary, we have the same conclusion as we did before, right? We know that the split graphs, the threshold graphs, the weakly threshold graphs, they have characterizations in terms of this Rao order. And because they have characterizations in terms of small Erdős-Gallai differences. And so if you were to look at the degree sequences of all split graphs in this Rao order, you'll see that they form a downward closed sub-poset. They're an ideal in this poset. And same is true for threshold weekly threshold graphs. So let's wrap up here. I would propose that given how many different places these have shown up, and given that a lot of the properties we observe in those different contexts can be kind of unified by looking at the Erdős-Gallai differences, maybe these things are worth looking at a little bit more. And so I would pose a couple questions. The class of threshold graphs is exactly the class of graphs you can get from starting from a single vertex and then iteratively adding one vertex at a time, so that the vertex you're adding is either adjacent to everything that was already there or adjacent to nothing that was already there. So you're adding either a dominating or an isolated vertex, and you just do that again and again. And any graph you get is a threshold graph. Now, if you look at the Erdős-Gallai differences, the effect of adding a dominating vertex is to keep the list the same, other than you sort of insert a 0 at the beginning. And if you add an isolated vertex, you don't change the Erdős-Gallai difference list at all. So those are some nice properties, but there are other things you can do to a graph that are not going to affect its Erdős-Gallai difference list, or they won't affect it so much. And so I think that it would be wonderful to take a look at which constructions or which operations allow you to preserve or to not modify too much an Erdős-Gallai difference list. In a similar, it's a structural problem, but maybe in a different direction. You'll remember that this decomposition you get that happens when the kth difference is equal to 0 happens, it's a pretty nice decomposition. I'm wondering if we were to consider other differences other than 0, could we maybe refine this decomposition even further and be able to say something nice about the structure of just general graphs? And then I'd certainly not complain if somebody were to find another application or another occurrence in the literature of these differences. If you do stumble upon something like that, please let me know. But I'll stop here. Thank you very much.
Let's thank the speakers. That was fascinating.
Yeah, thank you. Thank you.
Yeah, I just loved it. Any questions?
I got to run, but that was great. Thank you very
Thank you.
much. I got some questions, so I'll have to email you.
I look forward to it. Thanks.